Now I come to the rationale between the two postulates of statistical mechanics and the, I already talked the ergodic hypothesis. So basic idea is that we do a huge number of interacting systems, and this 6n dimensional phase space that Boltzmann and Gibbs developed, Maxwell did not. Now, so this motion, just the question you asked, motion is determined by forces and the instantaneous positions and intermolecular interactions. That is where Hamilton's equation comes in. And so the path followed by the representative executing their nature, this is very important, this Kubo's language. We are a great stat mech guy called Rigo Kubo. Their natural motion. So what we are following is the natural motion of the system in the phase space. So trajectory is very important, no external force is there. Okay. So we want to establish now the relationship between such a microscopic trajectory. So a trajectory is a microscopic thing and measure properties. And this is, I could do that, I could calculate the pressure, but if I could do Newton's equation, hold the system, then if I could tell the atoms and molecules bombarding against just the way Maxwell did in his ideal gas, calculating the pressure PV equal to 1/3 mc square, I could do that, but unfortunately I cannot do that because I cannot calculate all these things, okay. That is why we are now going to do first, we do a ensemble time averaging. This is the time averaging that I already introduced, that we follow it for a long time. This is the kinetic energy mv square, the average over a time trajectory of each particle. This is exactly what I wrote down some time ago. Here I am just kind of recapitulating the whole thing. Yeah, well, a little bit of a problem, yeah, that should be, yeah, I think one has to do, yeah, this is always a problem, okay. So time average from theoretical point of view, it is impossible to generate a long term trajectory of a microscopic system with large number of particles, that I have been telling. So we had no other option but to go to a probabilistic description, the one that I described. Fortunately, the probabilistic description can be developed with the help of only two postulates and one hypothesis. That is the beauty of the whole thing. So then, that is, in order to do that, Gibbs came out, Willard Gibbs came out with the brilliant mental construction of ensemble, and that was really amazing. Though it was, one should remember that he followed the same ensemble which Boltzmann followed, which is NVE. So all these postulates, two postulates and the ergodic hypothesis are valid in the microcanonical ensemble. The NVE ensemble is called the microcanonical ensemble, as we will do more later. So this is a language is that the kind of uncertainty or the imprecise is the same statistical description. So this is an interesting thing again. As I am saying, recapitulating, the concept of an ensemble is based on the realization that a system at equilibrium must have a very large number of microscopic states. This is partly probably Macquarie. The natural motion of the system at non-zero temperature takes the system through a finite fraction of the states. There is a very delicate question here which we will deal much later, in a time that is comparable to time of measurement. It is very important. Even when you are doing experimental measurement, we are going through a very tiny fraction of the total sample space, very important. And there is a concept of cell similarity, and these things will come in to do that. Measurement of microbody. If you now consider the system remains at fixed energy at all these times, then the trajectory moves on a constant energy surface, that is the NVE. And according to the laws of mechanics, classical or quantum, and that generates the trajectory. But we do not need the detailed information. It is extremely important. We do not need the detailed information, at least for the ensemble based equilibrium statistical mechanics that Willard Gibbs developed. We do not need, that is again saying, but we need certain realistic understanding of this trajectory and realistic understanding of what we are talking of averages. And instead of taking the time evolution of the system or the microscopic states as required by Newtonian mechanics, we consider mentally a huge number of states, and as I keep saying, it is NVE, that is where whole this thing was set up. But going from NBA to temperature T is a little different thing. We have no control over microscopic states of the system, and neither do we want to have any control. We do not want them, but we want them to flow over the phase space. That is why equilibrium probability and ergodic hypothesis is important. The flow in the microscopic state, in the phase space, in the trajectory should cover a significant part of the system. Okay. So, ensemble represents a collection of mental replica and is called microcanonical ensemble. Trajectory system travels in a constant energy surface. All the points in trajectory are equally likely. That is what the, as I said, there are no other option, and good fortune of us that this works out okay. And actually, it was still very doubtful for a long time, even in 1950. There is a guy called who wanted to push Shannon entropy called James, who wrote to Uhlenbeck saying to making that okay, because of your difficulties StatMech, you should probably consider information entropy and this kind of as a mainstream StatMech. So Uhlenbeck gave the famous answer saying that since the Li and Yang proved that one can explain statistical phase transition within statistical mechanics, we do not need your Shannon entropy, and that turned out to be correct. We did not need that. So complete trajectory of the system can be obtained if we cancel n-body Newton's equation. That is the one partly we do when you do time dependent statistical mechanics, at the part of it. The trajectory we generate of the few tenths of nanosecond and few interval frame, and we time interval we dump it. Even then huge data is there which comes handy sometime. So this is kind go down with details of the understanding what, how could be the phase space can be quantified. The smallness parameter turns out to be Planck's constant, and this analogy is beautiful. But I am not going to go into too detail on that. Right now I just want to say the following. So these are the different kind of ensembles that I will do in the next lecture. So the main idea of this lecture is something which I am intensely fond of, is these two postulates, because I figured out to an extent the interrelation between the two postulates, the necessity of the postulates and the ergodic hypothesis only when I wrote the book. So all these things can be connected, and all this was done by, again it is very strange, the person who does everything, like Maxwell did everything of kinetic theory of gases, all the equations that you do undergraduate. Schrodinger did all the thing, and then Willard Gibbs did much of it almost alone there. So this time average and ensemble average, we all did that. One thing, as this question was asked, that when does, why, the problem is that this is of course a problem we worked out, that if you have a system like that, let us see it is stuck here, this is the energy landscape, and the particle is executing random walk here. And if it gets stuck here, then we simulate it, and we simulate it, and we simulated 4 years, we could not get a converged result. The guy who was doing was not stupid. That because this system, as you get is larger, then you face larger and larger barriers, deeper minima, and you are thrown out of the track. We never got converged result. This is the reason, this is the thing you need the ergodic hypothesis. If ergodic hypothesis, so this system is quasi-ergodic. Later I found out that there is a famous paper by Newman and Stein who said diffusion, and this is a beautiful paper by I wrote with Seki-san and Shoikot Banerjee that on this issue, but we were really put on the right track by Newman and Stein, two mathematicians, Santa Fe Institute and Courant Institute, saying that one dimensional random, this is called random energy landscape, diffusion in one dimensional random energy landscape is pathological in 1D. That exactly what turned out to be correct. So then postulate the equal probability, and then each state is visited equal number of times, so waited very long time, this equal probability, every state is equally probable, and then of course these two are connected, which is very very important. Two postulates tested are to be supplemented by ergodic hypothesis. These assures the practical validity of the first postulate. Without the ergodic hypothesis, your first postulate, as you were asking, is mute. Okay. Mathematicians and physicists, and this is done by books, sometimes called Boltzmann-Sinai, because Sinai is the one who first proved ergodicity for a system of hard disks like billiard balls, but on a 2D he did that. Real proof is amazing. It is the Bubinovich and Sinai, all mathematicians, system of hard disks is a beautiful, beautiful thing that was done. And so the ergot states that during its trajectory in phase space, the system is free to explore all the microspace. It has to be free. Here it is not free. That guy is not really getting stuck there. So it has to be free. Sufficiently long period of time, spends time in a state that is proportional to the volume of the state in phase space. That opens the room for NPT or NVT ensemble, where energy now plays an important role. So it's like that. I think I will stop here today. The measure of ergodicity and all these things I am not going to go into, but I think today, yeah, all these beautiful measures are there. This is essentially done by Dave Thirumalai and Mountain by doing the how it is connected to diffusion. It is given in my book, all the details things, and how you talk of diffusion is very interesting. As I was telling one of my lecture here, that you have to, if you want to talk of many body diffusion, whole system is diffusing, then you have this kind of quantity. That's what Thirumalai and Mountain used to show the breakdown of ergodicity as glass transition is approached. But that means you are not talking of one particle, you are thinking of whole configuration space of the system. All right, I think I'll, there are many other things, but I'll stop here. To recap, we started with probability and statistics, central limit theorem, and several other interesting things. Then we went to phase space, we went to trajectory, and we discussed two. Next, what will happen? We will do, starting with these postulates of, so in my book I talked about realization of promises. We now go from microcanonical ensemble to canonical and canonical ensemble. And then when you go to fluctuation, we start deriving the beautiful equations like mean square fluctuation, specific heat and all these things, and then the other systems will follow. Okay, any questions? Sure.
Well, you are considering this phase space and other things. You are always considering the position and movement.
Right.
So why not angular momentum and rotation?
Right, absolutely. So whenever you have orientation, the phase space becomes larger. Absolutely. So for example, when you are doing water molecules, you have the orientation. Sure. That you see, that at a level formal, that doesn't pose any problem. The reason is that you just expand you expand your notation. X now has position and orientation, and P will have now momentum, all kinds of momentum, angular momentum. So angular momentum's one reason is that it decays very fast usually. Its conservation hardly pose a problem. For that one, momentum conservation is also doesn't pose too much of a problem in most of our calculations. But yes, but the formalism part, nothing changes. See, this is essentially like in Schrodinger equation. You write down a wave function psi. You do not know when you are writing down Schrodinger equation of a many body system, you do not think of solving it at that point. You are writing and so all the theorem that you prove with a psi and everything, that is just it's just formalism to you, whether it has particle in a box or whether interacting systems and electron gas, nothing matters. So you have to, what I am trying to say, you have to separate out the formal part and separate out. I once I was the good friend of a friend called Jim Lill, who was developing a theory of scattering with John Light, theory, reactive scattering I think, called Lill light theory, and he was all the time writing this very difficult equation with momentum, angular momentum, position. So I always told him that, Jim, how are you going to put these things? He said, Biman, let me develop the formalism first. He developed the formalism, then he put in computer and it became a very famous theory. So when you are developing the formalism, you have to think of applications, but do not get bogged down by applications at that stage. So yes, to you, when you are writing down phase space or writing down these equations of partition functions, it does not matter whether your x has orientation or position.
Generalized position.
Yeah. You have to be able to think like that. You have to be able to think in a very formal way. But at the same time, back of your mind, you know when you are going to do applications, these formal things will become real things. And that happens, that much faith you have to have. Science is always for optimist people, science is never for pessimists. I have already told you that this is the third lecture, fourth will start with the partition function. And then Liouville equation is there, but I might not do Liouville equation too seriously. Liouville equation is the equation that allows you to track, to generate the trajectory in phase space. It is nothing but a Hamilton's equation. I am not going to do that. Instead, I will continue with the ensembles. I will go to fluctuation, and from fluctuation, which is a wonderful chapter, I tell you, that from there we will do monatomic gas and diatomic gas. But everywhere it will be very practical. Like when I do monatomic gas, I will want to tell you about the use of that in modern day real life problem like protein DNA interaction, dark DNA intercalation, and that has been used to find out the binding of chemotherapy drug daunomycin to DNA. And then again we go to see the very interesting thing is that entropy comes with the monatomic gas beautifully, but the concept of rotational vibrational entropy, those are very important things. Rotational entropy in molecule usually 30% of the total entropy, that comes through diatomic. And then all your guys like the normal modes, the fact that Cv is 3/2r, all these things comes from just a diatomic molecule. It's amazing that how much you can know from doing monatomic and just diatomic. Then we will do Isaac model, which is the first really. So monatomic gas we will do non-interacting, diatomic we will do non-interacting, first time interacting system we will do Isaac model. Okay.